All right, welcome to the final installment here on our discussions about groundwater in Virginia. This is the last talk, and it's going to be on basic groundwater concepts. We're going to briefly touch on the analysis of hydrologic information and how that can be used to help describe groundwater systems. And then we're going to briefly talk about exploration methods for groundwater and for just locating and describing the boundaries of the system, and also for locating viable aquifers. Imagine you all have seen this picture before. This is the hydrologic cycle. Just wanted to briefly make the point that there's a finite amount of water in the world, and it just circles around. It's either going to be tied up as surface water, lakes, ponds, streams, the ocean, or in the atmosphere, or in the groundwater system. And the groundwater system is a very small but very important component of the hydrologic cycle, mainly for us because it's an easy way to tap into potable or drinkable water sources or clean water sources because it's naturally filtered. Just to illustrate some basic ideas here, this is a very simplified cross-section of a confined aquifer in, let's say, the coastal plain. And this orange is clay, and this white is sand. And we have 3 wells here that are all drilled in the same aquifer, and they're open. This is a very important part to understand, is that they're open in the same portions of the aquifer. And the reason they're open is because there are screens in the wells. Since these are coastal plain wells, you have to advance casing all the way down through your aquifer and then screen it so that you can allow water in. This is a pressurized system, and because it's confined, so it's like a pressurized pipe. And what happens is when you drill a well, you breach the wall of the pipe, or you drill in through the top of the aquifer, and water level will rise in the well once it's built out to a level that is equivalent to the amount of pressure in the system. So if water level rises very, very highly above the top of the aquifer, that means the aquifer has a lot of pressure in it. Right now, these 3 wells are at the same pressure. They're in a system where pressure is essentially equal. But what happens when you pump this central well? Then you lower the pressure in this portion of the aquifer, but pressure out this way is higher, further out into the aquifer. And so you induce what we call a gradient, a pressure gradient, where you have higher pressures out away from the pumping well, lower pressures at the pumping well due to pumping, and water migrates from areas or travels from areas of high pressure to low pressure. And the rate at which the water travels is dependent on how hard you're pumping the well, and also the ability of the materials to conduct the water or allow the water to pass through. And also how severe the gradient is. If you have a high pressure gradient, the faster it's going to want to be pushed, basically, or the steeper the hill, that the ball can roll down. But it's also possible to have a very steep gradient and still very low flowing, small amount of water traveling through the system if the material you're trying to move it through is not very permeable. So there's a lot of factors at play here when you start to try and describe or characterize aquifer systems. You could have a very similar, this works in fractured rock too. The only difference is instead of a pressurized sand aquifer, you have pressurized fractures. So let's talk a little bit, and then same thing. You just pump it, lower the gradient, and water moves in response. So let's talk a little bit about how to analyze data, because you can get a whole lot of information from just the rate at which water level drops in a well in response to pumping. If you know how much water you're pumping or have pumped over time. And it's also very important, if you're going to do this, to pump it at the same rate. And you call that an aquifer test. And these types of tests are very diagnostic for describing important components of the system that you can then use to forward model or predict how an aquifer might respond to pumping at different rates or for longer periods of time, or if you put in an additional well, what that might do to the system, and can help you answer practical questions like that. Probably the biggest reason why people do aquifer tests, though, is just to make sure the well is going to hold up to pumping. You don't want to put in a big municipal well or city well that people are going to be dependent on, and then find out a couple years down the road, whoops, yeah, it's not going to hold up. So you do, that's probably the main reason why people do pump tests or aquifer tests. And the idea is to pump the well and stress it at a rate that is as high or higher than the rate it's typically going to be pumped at for a long amount, pretty long period of time, usually 48, sometimes 72 hours. So we're talking 2-3 days. And what we have here is an actual pump test on a pumping well. And you have drawdown in feet on the y-axis and time on the x-axis. And it's a linear scale, so meaning that time is spaced out evenly, and so is drawdown. And what you see is a whole lot of drawdown early on in the test. Like the first 500 minutes, you got 110 feet of drawdown. And then after the first 500 minutes, you've got, so let's say that's 110 and it stops at 130, so only 20 feet of drawdown. In order to really get anything from these data, you have to know what part of the curve to analyze, and it's usually the later time part of the curve when the entire aquifer is being stressed. And you can take that rate of drawdown over time and back out some important parameters. But usually what you do, if you do that, is change the scale on the x-axis. So this has gone from a linear scale to what we call a logarithmic scale, and it's just a different way to subdivide the units. And these units are now based on units of orders of magnitude. So 1 minute, 10 minute, 100 minute, 1,000 minutes, and they're subdivided into tens. So this is 100, 200, 300, 400, 5, all the way up to 1,000, 1,000, 2,000, 3,000, 4,000, 5,000. The part of the data that we're mainly interested in is this part, the late time linear part, because that's telling us the well is behaving, drawdown in the well is representative of an aquifer that is being fully stressed and is responding radially, meaning that the gradient is moving away from the well in a radial sort of sense out into the system. And so this is the time period you want to analyze for really describing the system. And it's important to note, because this is a log scale, this time here to this time here is the same amount of time as from this time here to this time here. 1,000 minutes here, 1,000 minutes there. So this is a lot of long time period we're talking about right here, even though it's short on the graph. All right, and then, you know, this line, I just put this line in to represent a linear, the fact that the system is drawing down in a linear sort of sense now, and that's a radial flow condition. And I don't expect y'all to, you know, really remember any of this, but I do want to make the point that these curves or these data are very diagnostic for helping us understand the system. Now let's pretend we pumped it for 3 days now. There's the start of the part of the time where you want to really analyze, and there's the ending part of the time. But let's just pretend we keep on pumping. And what happens is, okay, this is the start of radial flow. The aquifer radial flow is propagated further out into the aquifer now, and we stop the test. But let's pretend we keep on going, and all of a sudden the drawdown increases. It's drawing down at a much faster rate all of a sudden. Well, that's a clue that it has hit the drawdown. It's a clue that there's a boundary that's condition that's been reached somewhere in the system, meaning that it's it has stopped looking out in some sort of the portion of the aquifer system. It can't find water, it can't expand out any further, so it stresses the part it can already access even harder and causes drawdown to occur. And that's a very important clue to folks that are analyzing these and are responsible for trying to describe these systems. You can also have the opposite thing happen where you hit what's called a recharge boundary, and that's where the stresses, the gradient has propagated far enough out into the system where it has found a new source of water. And it could be something as simple as maybe a breach in the confining unit that's allowing water to leak down from saturated overburden, or it could be a river or something that is incised into the system and it's actually pulling water out of the river and causing extra water to be drawn into the system. And so drawdown doesn't proceed at the same rate it has been. It actually slows down. That's another important thing to know, because right now, when you do a pump test, you know how the system behaves when it's stressed, but you still don't know anything about the dimensions of the system. And so to do that, you know, if you really want to define the dimensions of the aquifer, you have to use water levels, geology, and geophysics to figure out the size and shape. And so we'll start with water levels. These are all water levels, and you can see what kind of scale we're at. This line is 5 miles, so it's a pretty big area. And they've gone through and taken water level measurements in all these different wells. And then what you can do with that is contour it. So you put in, where's the 600 elevation for all these water levels? And you can use the measurements to help define where the 600 elevation is, and then 650, 750, 800, blah, blah. So water always moves from high to low elevation. That's just kind of the rule. So from this information, assuming you're in the same aquifer, you have learned that water is moving from like 950 down across here and on out, and it's probably discharging into this stream right here. So that's one way to help define an aquifer system. It's a very important way. Another way is describing the geologic materials in the system. You know, well cuttings, core analysis, looking at outcrop that may help you define or establish features like no flow boundaries or recharge boundaries just by looking at the lithology and the geology of the system. And you've seen this core from the coastal plain talk, this is Potomac Aquifer sands. I forgot to mention this, but this is all core material. It's been pulled out in a tube and extracted. And that's how you learn about the geology in a lot of the coastal plain. And these are chips, rock cuttings from air rotary drill rigs of different, this looks like a granitic rock, and that looks like a sandstone. And if you look real closely, this is a granitic rock here. You can see actually different minerals in here, biotite, feldspar, quartz. That is also a clue as to how the aquifer may be oriented or constructed, for lack of a better word. Geologic maps, big help in helping to conceptualize how groundwater might be stored or moved through a system. Here's an overview or a plan view. You know, you're looking down like a bird in the sky onto the earth. There's two different rock types along a fault. And so as a geologist, you know, one of the first things you'd question is, well, how does that fault, how can that fault act hydraulically? Does it act as a hydrologic feature in the system? And you can test that. And this is a cross section of the same map. So that is just a way to help you define the box or the boundaries of the system. And then geophysics. This is borehole geophysics. That's just a way to directly and also indirectly measure properties of the rock that the well has been drilled through. By lowering a series of probes down the well, you can figure out a whole lot of stuff about how fractures are oriented, what parts of the system are transmissive, meaning what parts of the system are able to pass water or store it. This is a surface electrical resistivity profile. This is, you basically put in a series of electrodes and run a current through the earth, and you measure the resistance of the earth materials to pass electricity. More resistive materials mean that they're probably less saturated, because water is a very excellent conductor. So very low resistivity zones, especially low resistivity zones at depth, may be a clue as to where water may be in your transect. And usually, you know, these can be on all different spacings, but usually these lines are a few, you know, 1,000 feet or a few hundred feet long. And if I was going to drill a well, I'd maybe try right there, see what happens. And as you can imagine, you know, trying to find groundwater isn't just, you know, hey, let's run the line, put a well in, you know, see what happens. You know, we'll get a ton of water, and a lot of times it doesn't work like that. You just got to keep scratching, keep looking until you find what you need. But these can be very useful tools for guiding well placement. Aerial imagery, very important, not expensive. So it's usually one of the first things people go to when they're trying to figure out a groundwater system, looking at aerial imagery. And recently, check this out, they've come out with LiDAR imagery, which is measured elevation data that's collected by shooting a laser, bouncing a laser off the surface of the earth and getting the refractions from the laser to get really precise elevation measurements of the surface of the earth. So I'm going to show you LiDAR imagery of the same area. It's not an exact overlay, but here's a pond, and here's another pond. And so this is LiDAR. Here's a pond, the same pond. This is the other pond, and you can really see, this is what's called like a bare earth image, bedding right in here. Just alluvial fill in this stream that was not apparent at all on the aerial imagery because of trees and vegetation and so forth. And the LiDAR allows you to strip all that away and really just look at the Earth's surface. And you know, these are streets and houses, and LiDAR has a whole lot of different applications: archaeology, engineering, geology, tons of stuff that I'm not even aware about. So very, very cool feature. But you know, so what? We do all this stuff. Why do we do it? Well, aquifer analysis and exploration allows us to answer questions about sustainability of groundwater and the occurrence of groundwater, so that we can better manage it, or just seek it and know where it is for future use. Analysis and exploration also allows you to keep developing a conceptualization of the system that will hopefully allow you to do things like predictive analysis. So like, what happens to the system if you pump it? Where if there is a contamination event, say a gas tank leaks into the ground from a gas station, where is that contaminant going to go? You can't answer that question unless you have water level information, permeability data. You know, somebody wants to know, where's it going? How fast is it going to get there? You need the data to be able to answer those questions. Source water protection, that has to do with knowing the dimensions of the system. You know, say you have a very important municipal well that lots of folks are dependent on, and you don't want it to get contaminated. You need to know where it's pulling water from, so that your zoning can be tailored in such a way that you don't allow building of, like, you know, nuclear stockpiles or, you know, waste dumps or anything in the area where you're pulling water out for your municipal well. So thanks for hanging in there. That concludes all the talks. I hope you learned something, even if it's just something small. And that's it. It's been a pleasure.